Looks like we're going live. Excellent. All right, still need to get the screen up. Let's see here. Avery, Rachel, Calvin, Odessa, Sophia, Eva. All right. Let's get this open. All right, so you probably received a notice that I've got data in biology posted. All right, this is RMD file, butterfat, jobs graduation. It's going to give you practice making histograms, making tables in R. So a lot of the same stuff that we were doing in this presentation. So you can start on it if you wanted. It's going to be due on Friday, just anytime during the day, and I believe I had it set up. Correctly. So I think I had it. The first one was I messed up, but I believe I have it set up for multiple submissions. So if you upload the wrong file, you can easily just correct it and re-upload it. If it doesn't, just let me know. I normally do that. So if you realize you did something wrong, or if you had questions, about how to do something and you uploaded the homework so that it was on time, and then we talk about it in class and you're like, oh, I didn't do it that way. It gives you an opportunity to go back and fix your mistake and get it re-uploaded. So I have that due on Friday, and then go from there. All right, that's posted on Blackboard. As I'm opening this stuff, my dad is not very computer literate, and he doesn't have the patience to figure stuff out. So I troubleshooted a printer issue on Windows 10 with him, and it was actually not his fault. So I don't know if you guys will ever encounter it, but he went to print it, or my mom did, printed it, and nothing worked. It didn't print. So you do your classic thing, turn off the printer, restart it, reboot the computer. None of this works. So then we find out when you go to the printer settings, add remove device or whatever, it has this printer, and then it had like 8 copies of this printer. So you remove the 8 copies, and then when you reboot the computer, they reappear. All right. It's you find it online. People talk about having this problem before, and if you do, I figured out how to solve it. So it's actually a corrupt registry. You have to go into the registry and delete all of those keys, and once you do, then you can actually remove all the devices and get things working again. So, and it took like an hour and a half, I don't know, 7 or 8 restarts just to see if it was going to work. Like ridiculous. And then you find the form where people describe the problem and the Microsoft tech comes on. Thank you for contacting Microsoft Help. Please do these steps, and it's the exact same steps that people already tried. Yeah, thanks. You're a real big help. All right. So let's continue this. So we did bar graphs, right? Now let me open up our studio too. This opened up. All right, so we did bar graphs, qualitative data, and then the point with this is that these bar graphs really emphasize the discrete nature of our data, or the categorical nature, because the bars don't touch. We have the spaces between them. And that's pretty important. That's pretty important for us because we don't really want to be deceptive in how we illustrate our data. All right, some people are, but we don't want to be deceptive. All right, so what do we do about quantitative data? All right, so with quantitative data, and this includes like some of the discrete data, we don't really want to use bar graphs. We don't want to use bar graphs because we want our bars touching. We want to emphasize more of the continuous nature of our data. So our options here is to use a histogram. All right, now the histograms are really easy to make in R. The function is hist, H-I-S-T. And that function will take a vector, okay? So we already loaded in, or if you open up RStudio, I'm gonna bring mine over. As soon as I can find my cursor. There it is. All right, so we've got the environment, all right? We already made the bar graph, and now what we wanna do is do our histogram. What my heading was. It's here. Bonus, making a bar plot. This is number 2. Making histograms. Okay. Function is hist x comma breaks. All right, that's our function. Oops, I won't use the arrow here. So where x is a numeric vector, x is a numeric vector, and breaks is essentially how many bars to graph. And you'll see the effective breaks. Right? So it's a very simple function. Hist, the vector. All right. By default, R will look at how many samples you actually have, and we'll try to come up with a good number of breaks to produce a pleasing histogram. But sometimes you want the histogram to have more bars. Sometimes you want the histogram to have fewer bars. All right. It just kind of all depends on the underlying data on your data set. Hit enter, bring those up a little bit higher. All right, so here's our markdown. I have an example here. We want to do a histogram of our plant data. So this was in quant data. All right, and if I just ran it now, it's going to fail. It's going to give me an error that I can't find it because look at my environment, it's empty. But that's okay because I'm working in my R markdown, and if you did things correctly, I can always go back to this chunk where we read in our data, all right, and I'm just going to run it. And voila, I have quant data now accessible. So here's our example of the histogram of plants. So I do hist, quant data, $ plants. And when I run it, you will see that R produces a histogram. Now there's other options with this figure. And if you're making a figure for a poster or for a presentation and you want to clean this up, come talk to me. I will gladly help you get this thing adjusted. I own a book called R Graphics. That's all it talks about is adjusting, how the figure looks. All right. I mean, that's almost an art in and of itself with all of the code. But there are things built into the function that we could automatically change. We can change the heading, the title. We can change the axis labels. We can change the font. We can change if these are empty, just basically white bars. We can add color to the bars. We can do a lot of different stuff, a lot of different things with this. All right, but this is basic. We didn't have to specify the breaks because R looks at the data set and says, how many samples do I have? What's my range? Let's try to get a decent number of breaks in here to make it pleasing. In this figure, you can see that our breaks happen at the whole numbers. So we've got a bar between 0 and 1, between 1 and 2, 2 and 3, 3 and 4, 4 and 5, and so forth. All right, so that's pretty simple. But what happens if we want to change it? What happens if we want to change the number of breaks? Well, very easy to do. I just add breaks equals and give a number. Let's say I want 3 breaks. I don't know why you would want 3 breaks, but perhaps you want to see 3 breaks in it. Now that's not 3 breaks. 2 bars. Basically 1 break. What's going on? R takes the number that you supply it and tries to do its best to give that number that you ask for, but it recognizes that sometimes it's almost impossible to get a graph that has these breaks. Now, is it technically impossible? No. R looks at it and says, it's not going to look very pleasing. Let me do the best. So sometimes it'll be fewer breaks than what you specify. Sometimes it'll be more breaks than what you specify. So, if I change this to breaks equals 2, this could very well be the exact same graph. And it is. If I do breaks equals 4. Now, did breaks equals 4? That's closer to 4 breaks. You get 5 bars, 4 breaks. All right? So don't panic if our breaks doesn't quite work. All right? I'm going to take that out. So I've got my histogram. So moving forward. All right, so making frequency distributions. How does this actually work? Well, if we have qualitative and discrete data, it's pretty self-explanatory. All you have to do is just take your frequency table, take the number, the frequencies of each of your categories, or each of your counts, the counts of each of your numbers, all right, and then do your histogram from that. Occasionally, though, you might have very large number of groups, and you have to combine some. All right, we probably won't have to do that. If we have quantitative data, now we're talking about continuous data where we have decimal points, and how do you go about doing that? Well, I'm going to say use a stats program, use R. R will do everything for you. If you wanted to do it by hand, this is basically how you do it. You have to figure out first how many groups do you want? How many bars do you want? And then from those bars, you have to figure out what your groups will be, and that's referred to as the bins. So each of our bars represents a single bin. All right, and then once you know what bins you want, then you have to take your data and put them into those bins and get a count of how many of your data, or how many data points, actually fall within those bins. And while you're doing this, we want to strive for 12 to 20 bins total. So you can see that if you do this by hand, this is actually kind of difficult. And that's why I said, if you're going to make a histogram, give it to R. Because our function, hist, our numeric vector, and then we can specify the number of breaks, number of bins to use. All right? So that's all up here. Let's do our histograms and demonstrate this breaks function. So with our breaks, we want to have a graph that has the number of bars that is just right. Too few bars will hide a lot of the information that's in the data set, will hide a lot of information about the distribution. Too few will start giving us a lot of error associated with it and might make it difficult to make conclusions about the distribution. But if we have just the right number of bars, it'll be very easy to tell. So what we're going to do is run this code. And I'm going to step you through what each of these lines does so that we can see it. All right? And what we're working on is, as we move forward, as we get to our stats, actual statistical tests, one of our assumptions is that our data are normally distributed. And one way in which we can assess normality is through a graphical method, is to look at a histogram. Is it the preferred method? No, it's actually not at all. It's not a preferred method because it's just kind of arbitrary in our distinction, but oftentimes we can do a histogram. So what we're looking for is a bell curve. That's what we're looking for. Does our data follow what we would classify as a typical bell curve? So first up is we're going to generate our random data. all right? So I'm going to use this function here, this first line, all right? So who can take a guess at what this line is going to do? If I say verbalize what that line does, how would you answer?
X is a random assortment of numbers between 0 and 1,000.
Good guess. Good guess. Not quite right. But you did say x is going to be our variable, so that's good. So we're going to run this function, and then whatever it does, we're going to save it as the object x. All right, we've got that. We haven't encountered this. This is our norm. All right, our norm refers to the normal distribution, and we're going to encounter all of these different distributions. So we'll see poise, we'll see binom, we'll see n binom, we'll see chi-square, we'll see f, we'll see t. All right, those are all statistical distributions. The letter in front of it can be r, d, p, or q. All right, this one is r because it's saying we want to generate a random number from the normal distribution. All right, and the question is, how many random numbers are we going to generate? 1,000. All right, so this will be a demonstration of breaks. It's going to be what we will be typing in. So this section will investigate the bell curve shape of a random set of data. Okay, so first we generate our random data using the R norm function. Okay, so R norm x generates x data points. So however many data points we want, that is in our x part. All right, that's in our parentheses. We're going to generate x data points, x random data points. That's the R part of it. From the normal distribution. Default is mean equals 0, d equals 1. So if you did a search, the help file of R norm, you would see mean and SD in there. We haven't quite made it there yet, but you've probably encountered means, averages, and you've probably encountered standard deviations. All right, that's what it is. So as we learn about our probability distributions, this is one. It's continuous distribution. We have an infinite number of curves. And the reason is that this curve itself is defined by the location, which is a mean, and by its dispersion, which is a standard deviation. So what we're going to do is just generate 1,000 random data points from the normal distribution, and it's going to have a mean of 0, standard deviation of 1. So we are going to run that. And we're going to save it as x. Oops. R norm 1,000. I run it, and now x appears. All right. So we want to know, does this actually follow the bell curve? All right. The default actually does a pretty good job. So if we just do default hist of x and run it, it does a pretty good job. All right. When we look at it, does that kind of look like a bell curve? Yeah, it kind of looks like what we would typically think of as a normal bell curve. All right. So let's mess around with things. Breaks equals 4. Hides too much information. All right, so first we're going to do breaks equals 4. Hist of x breaks equals 4. And you can see it took this 1,000 data set, 1,000 data point data set, and instead of having 20 different breaks, 20 different bars, we've said we only want 4 breaks. And this is what it gives us. It actually gives us 4 bars. All right? Does that really tell us if this is a bell curve or not? Not really. I mean, we've got 2 bars that are kind of high and then 2 bars that are low. I mean, it can look like a bell curve. So you're going to have to move our camera. So that's what our graph looks like. Let's move this up. Those watching in their office upstairs can see, hopefully. Man, it's dark. Move in a little bit. And let's zoom in a little bit. All right, so here's our curve. Our bell curve should look something like this. All right? We don't know if it looks like that, or what if this actually looks something like this? Could be a normal distribution, but we don't quite know. What we've done is taken all of those data points that are kind of in this shoulder area, and we've just grouped them. We just kind of threw everything together. So breaks equals 4 doesn't quite work. I think there's way too much information that is lost when we combine the breaks equals 4. What happens if we do breaks equals 300? So 300 breaks is going to give us an average of about 3.5 data points per bin on average. So our breaks equals 4 gives us an average of like 250 per bin on average, but we know that that's not the case because we have, like 450 in these 2 bins and then like 50 in each of the remaining. So breaks equals 300 is too much information. And that's pretty easy to demonstrate. Just do hist of x and then breaks equals 300. And again, with all of these breaks, could we fit a normal curve on there? Yeah, we probably could. It's going to be just, whoops, covered up here. Find my cursor. It is. Sorry, those of you watching. There, breaks equals 300 is too much information. Here's our graph. So you can see we've got a bunch of bars up there. All right, it looks like you'd see it and you'd think these points here. Well, we should be up higher, but we've got all these low points. All right, these look like they're way too high. So you might say, yeah, this isn't normally distributed. But in reality, I mean, it's just random variation. This could be rounding, and for all we know. So when you look at something that's just the default, it looks actually pretty good. It looks pretty good. If we needed to go a little bit more, we could. So if we say, yeah, I think I'd like a few more, go ahead and try a few more. We start at maybe like breaks equals 10. Let's try breaks equals 20 and see what that looks like. So, let's try it. Check out breaks equals 20. Hist x. That looks like that didn't change. Looks like the default. Let's bump that up to 25. See, that changes. That's a little bit better. And I'm going to update that to 25. A little bit more detail in our data set. All right, we can see some of the peaks and the valleys. But it still kind of looks like it's a normal curve. Kind of looks like it's a bell curve. And it should be. We drew it from a normal distribution. All right. Questions? Problems? Pretty easy. Histograms are pretty easy. They really are. we're going to be doing histograms throughout this class. All right, so here's an example. I gave you a data set. Here's an example. You've collected these data, and we want to know what the histogram looks like. All right, so just practice in R. Get these data into R. So make a vector of these data sets and do a histogram and see what it looks like. And we're not going to do this by hand. If you do it in Excel, the data analysis package actually has a histogram function in there where it would automatically bin it for you. But if you didn't have that package, you have to go through the process of binning everything, and we're just not going to do that at all. So we're going to use R, make it better on this. While you do that, let me get mine in the first. Made it easy on you guys to actually put these in numeric order. So, as you're working, what do we have to do first? What do we do first? Make a vector. All right? How do we make a vector? With a C, the combine function, right? Is it a capital C or a lowercase c? Lowercase c, right? So C parentheses, and we just type these numbers as is, like this? Copy and paste it. What do we have to do? Separate them with a comma, right? Separate every value with a comma, all right? And then we're gonna save that, right, as a vector. What did you call it? Call it anything you want. I called mine prac, P-R-A-C. And then once we have that vector, what do? We issue the hist command, right? Issue the hist function. So here's mine. Here's mine. Hopefully yours look just like that. I do histograms a lot. Because I'm going to show you something different. Gonna run. What happens if I get a histogram like that? Data entry problem. All right. Common mistake. It happens. You forget a decimal point. All right. Are you really going to use the histogram for any sort of data analysis? No, probably not. But one of those good first steps, those good practices when working with data, is just to look at your data, visualize it. Oftentimes the graph will reveal a mistake like this. and then you catch it early, because the last thing you want to do is, leave that as is. I don't think I ran that yet. Let's double check. I did. Yeah, let me leave that. Take that out, rerun it, and then you run it. You didn't look at it, and then you say, "Oh, let's take a look at the mean of this." And I get a mean of 7.39, and you go to your professor and say, "I've got an average of 7.4. So this looks bigger than what we measured in another pond. Maybe there's something significant." And then you go on a wild goose chase looking for this, only to find out that, yeah, there was a mistake here. When we get it corrected and we run it, and then we go back and take our average, you actually see average is actually 4.65. Big difference. All right? All from a data entry. You would have caught that very early on. Just take a look at the data, see what it looks like. All right, so that out of the way. All right, so stem and leaf displays are an easy way to do one by hand. All right, this is actually described by Tukey in 1977. I still teach it because sometimes you're out in the field, you've collected data, and you just want to take a quick glance at it. And this is a very easy one to do by hand. You don't have to bin it. You don't have to do anything. You just make your stem and leaf diagram. All right. There are tutorials on how to use it. All right. R has a stem function that allows you to make a stem and leaf display. Are we going to do it? No, we're not going to do it. I'm not going to introduce this at all because basically all of our work is going to be on the computer. So it'll be histogram. Use the hist function. If you're curious on how to do this, you can do a search, or you can stop by my office and I'll show you how to do a stem and leaf display. There's only been a handful of times when I've done these like in real life, like outside of a class. And all the other times I've been had access to a computer, and that's what I did. I just used the histogram function on the computer. It's about the only time I did it. So yeah, if we weren't doing any of the online stuff, yeah, I'll show you how to do it. It's pretty quick and easy, but we won't. Any questions? No? All right. Let me get the next one. All right, so we introduced data. All right, data in biology. We have our variables. We've completed everything that you need for the homework assignment. And now, what we're going to do is move on to descriptive statistics. All right, summarizing our data. We've already kind of started looking, learning about how to do the visualization. Look at a histogram, look at a frequency table. All right, those are visual summaries. What we want now is a numeric summary of our data. All right, and this numeric summary is simply field of descriptive statistics. All right, so when we describe our data, there are two things that we need to describe. We need to describe its location, and we need to describe its dispersion. All right, so our location is simply the central tendency of the data. Where do most of the data fall? All right, that's our location. That's our central tendency. If you think about location a little bit more, you can think about our data, that whatever measurement we've taken is falling along a single axis, all right, where we are bounded perhaps by some upper or lower value, or our values are negative infinity to positive infinity. Our location tells us where on those range of measurements most of our data will fall. All right, so that's our location, and the primary one is central tendency, so mean or median. All right, dispersion tells us the variability in our data. All right, so it tells us how much variation we actually have in our sample. So location tells us where along our measurement axis we fall, and then the dispersion tells us how wide is our data on that axis itself. All right. A lot of times this dispersion can be referred to as a scale or variability of our data. And there's a couple of measurements there. So what I have here is just a graph with 3 different lines on it. And I know that the camera kind of hides some of these. That a little bit. All right, so the black line is kind of like a normal curve. I actually don't think it's a normal curve line, but kind of looks like it. All right, so we have a measure of central tendency. That is our peak. That's where our peak is. And then our measure of dispersion is how wide that area is. All right, compared to the blue line, the black line has a smaller location, so it's left on that x-axis. And the blue line has much more variability. It's much wider in its spread. What about the red line? Yeah, you can see our location centered at a different place. All right, our location centered at a different place on our axis. All right, and our spread is wide. Is it as wide as the blue line? Visually, it's kind of tough to tell. But what I'm gonna show you is how we can actually make these comparisons, how we can compare the variability in our data, the dispersion, how we can compare the location of our data, so doing tests of means and so forth. All right? So first thing we're gonna do is generate some data. Oops. Things are moving. Live feed's going crazy. Apologize. Sorry. All right, so we're going to generate some random data. So this is going to be for this presentation. All right, and I think we also have some data that's also posted. All right, so what we're going to do is set our seed first. Right? So with our random data, what this function is going to do is set the starting place for our random number, which is kind of interesting. You say, hold on, how can you have a starting place for a random number? Well, a computer is more of a pseudo random number generator. If we wanted truly random numbers, what we would have to do is create like cards and then just randomly throw out the cards. That's random. All right, but with the computer, what it's going to do is uses an equation to start getting a number. All right, and whatever number it gives you, then that number is the starting place that feeds as the input into our equation to generate the next random number, and then the next random number over and over and over and over again. All right, so if we all started with the same seed, with the same starting number, then we are going to end up with the exact same vector. All right? So what I'm going to do is I'm going to go back to R. So our RStudio, all right? This was data in biology. I'm going to make sure I save that. All right? And that is basically done. So we finished off that presentation. I'm going to create a new markdown. All right, this is 03 descriptive statistics. All right, create a new one, and this will be the new one to go with our summary statistics. All right, so just delete all that, start fresh. All right. All right, so we're going to start with random number generation. All right, that's what we're going to start with. Random number generation. Right. Oops, let me get my cursor. Run this. Bless you. We are going to do this. Round, parentheses, run if, RUNIF 10 min equals 0, comma, max equals 10. Okay. So get it in there and then run it. These are my numbers. 6, 8, 9, 10, 2, 2, 9, 2, 9, 2. So let's think through this. All right. So we didn't really talk about this, but we have already seen our norm. So this is kind of similar. All right. We're going to generate a random distribution. We're going to draw a random number. How many numbers? 10. 10 random numbers from the uniform distribution, UNIF. All right. And what we've done is specified we want our 10 numbers to come between the numbers 0 to 10. Those numbers, it's a continuous distribution. You could take any number between 0 and 10. So we're going to round it, and the default is to round to the whole numbers. So I get this. So how many people got these exact numbers? No, you didn't. All right. And if I run this again, you're going to see I get a different set of numbers. I run it again, I get a different set of numbers. That's all part of our number generation, our random number generator. So what did R do? Well, when we called the very first time this random number generator, R looks at the system time and uses that as a starting point for its equation to get our random number. All right? We have to be, if Nate and I wanted to get the exact same numbers, we had to start fresh, start a new R console, had to get the code in, and then at exactly the same moment, we had to press enter. How likely is that? No, not very likely, because our system clock is running at like millisecond levels. Right? We have to have exactly to the millisecond, if not, I think it's even finer than milliseconds, exactly at the right time. So how do we fix this? Because what we want to do is when we generate these random numbers here in this class, at least for walking through and doing demonstrations and the presentations, we want to ensure that everyone has the exact same numbers. So when you run it at home, you're getting the exact same graphs, the exact same stats, everything. So to do that, we are going to use the setSeed function. The set.seed function provides a starting place for the pseudo random number generator. The result is an identical sequence of numbers every time. I guess that's one word. All right. So what I'm going to do is set.seed. All right. Pick a number. Rebecca, give me a number.
14.
What's that?
14.
14. Small number. That works. All right. We're going to set the seed, and then I'm going to copy and paste this code again in here. And I'm going to run it. And those are my numbers. You run it and tell me if you get the exact same numbers. Get the same numbers? Yeah, we should. We should. Okay. If I run this again, I get the same numbers. Get the same numbers. Over and over and over again. All right? It's a pseudo random number generator. We gave it the starting point, gave it 14, and then from there, we get the exact same sequence of numbers. This is really good if you are doing an analysis that's say random number generations or randomization tests, and you want to have a repeatability of your results. We can set the seed, then whatever that seed is, that's the starting point for our random number generation. Now, here's the interesting part. All right. So I ran that set seed, and then I ran the round function. That's what I want, so that I start here. If I go back and run this one again, I get a different set of numbers. This basically is that next number, right? So I got 92599744796. All right, that's up list. I generated 20 total. Run this. 92599744796. All right. So there is going to be a time, and we're going to introduce the set seed function. All right, where when we generate our data, I'm going to have the number generation basically in a block. I'm going to recommend you do the same thing. We'll have our set seed right at the top, and then each of our random number generating functions, one after the other. So that is what we are going to be doing. So what we're going to do is stop here. All right. On Friday, I will introduce the distributions that we're going to use. These are going to be very brief introductions, basically explain what these codes are doing. And then you will see, we will get basically this block into a chunk so that when we run it, we get the exact same data points, or we make the exact same vectors as the ones that I used in the presentation. All right? Don't forget the homework. Work through it. If you do have questions, bring them to class on Friday. All right, we'll answer them at the beginning. You know, if you messed up or had trouble trying to figure it out, then we'll answer it, and you can always upload it later in the day. I think I gave the deadline at like 11:30 at night, so you can always upload it later. All right. Yep.
On that homework, when it says to make a frequency table, do you just mean the kind in R, or do you want us to make one in Excel?
No, you can just do the one in R. Yeah, so in R, it wants you to make a frequency table. Don't make it in Excel because you're not going to be able to get it back into R Markdown. Write the code, have it generated in R, and then I know you did it. All right. Have a good one.
You find out any info?
I forgot.